Winkler method. In this video, we're going to talk about the concept of the biochemical oxygen demand, what that means, and how we can use the Winkler method to calculate that value. So the biochemical oxygen demand, or BOD, is used as a measure to determine the level of pollution in water. And it's based on the fact that in polluted water, you will generally have various organic contaminants. And the concentration of these organic compounds can be used to measure the degree of pollution. In more polluted water, you would expect to have more of these organic compounds. Now, it's hard to measure the concentration of these organic compounds directly because all of these organic compounds are going to be slightly different. They're going to react in different ways. They're going to need different methods of detection. But one way that we can get sort of a general idea of how much or how little of these organic compounds are present is using the fact that microorganisms have evolved in many cases to break down these organic compounds in water. But in order to do so, they need to aerobically respire. So they can get the energy from these compounds by aerobically respiring, and aerobic respiration requires the oxygen dissolved in water. Those microorganisms will use the oxygen that is dissolved in that water. What that means is that if you incubate a vessel of some sample of polluted water with these microorganisms in that solution, as they break down those compounds and they use oxygen dissolved in the water, we'd expect the oxygen concentration in the water to decrease because it's being used up by this aerobic respiration process. And that decrease in oxygen concentration over a set period of time as a result of these microorganisms breaking down organic compounds and using oxygen is known as the biochemical oxygen demand. It's usually measured in units of ppm, and if there are more organic compounds in solution, that means that your microorganisms will work harder, they will break down more compounds, and they will use more oxygen. So we expect the biochemical oxygen demand to be higher for more polluted samples. So, for example, untreated sewage would be somewhere between 200 and 600 ppm. So the change in oxygen concentration you would expect to see if you ran this experiment on untreated sewage would be 200 to 600 ppm. That's incredibly dirty. If we are looking at sort of a very clean, unpolluted river, that would be less than 1 ppm. That's safe to drink in this case. Untreated sewage, definitely not safe to drink. So you can see these measures can be quite important because they can tell you how healthy a sample of water would be to be consumed. It can tell you how effective your treatment has been. You can measure the biochemical oxygen demand before you've treated the sewage and after you've treated the sewage to see how much cleaner it is. So in order to measure the biochemical oxygen demand, we need a method for measuring the oxygen concentration in water before and after it's been incubated for a certain amount of time with these microorganisms. And that's where the Winkler method comes in, and this is really why this topic is situated in the redox part of this course, because the Winkler method involves using a series of redox titrations in order to find the oxygen concentration. You do this before incubation with microorganisms and afterwards, and you measure the difference in oxygen concentration. And really what this is about is converting oxygen in solution into a related amount of something that we can actually measure using a titration. So what goes is the water sample first is placed under incubation, and manganese chloride and alkaline sodium iodide are added to our water, to our sample of water. Under these alkaline conditions, Mn2+ reacts with our OH- ions to form manganese hydroxide as a precipitate. However, that precipitate is then oxidized by oxygen dissolved in the solution. The manganese is in excess in this case, which means the manganese hydroxide is in excess, which means the amount of MnOH3 that is formed is related to our limiting reagent, i.e. the oxygen. The water is obviously not going to be our limiting reagent because that's a solvent. There's a massive excess of that. And from the stoichiometry of this reaction, we can draw out that 4 times the concentration of O2 is equal to the concentration of MnOH3. That's just because 4 moles of MnOH3 are formed from every 1 mole of oxygen. Then just before analysis, we acidify this solution containing our manganese species, our sodium iodide. When we acidify, our manganese trihydroxide is neutralized. And that Mn3 plus then reacts with the iodide from the sodium iodide to form iodine. So 4 moles of oxygen made 1 mole of manganese trihydroxide. 1 mole of manganese trihydroxide made 1 mole of manganese 3 plus, and then 2 moles of manganese 3 plus made 1 mole of iodine. Following those ratios through, we can say that 2 moles of oxygen makes 1 mole of iodine. Now, the reason we have converted our oxygen into a related amount of iodine is that there is a simple titration using sodium thiosulfate that we can do to determine iodine concentration. In this case, we use thiosulfate, reacts with iodine to form S4O62- and iodide ions, and we can use starch indicator here. And that starch indicator gives us a color change when all of the iodine has been used up. So we can use this final titration to find the concentration of iodine in our solution, and we know that whatever the concentration of iodine is twice the concentration of oxygen. That is our measure of oxygen concentration. If we do this reaction before and after incubation with the microorganisms, we can find the difference in oxygen concentration, and we therefore have the biochemical oxygen demand. Okay, key points to take home from this video. We saw that BOD can be used as a measure of the degree of pollution in a sample of water. It depends on the rate at which oxygen is used up by microorganisms to break down organic compounds through the process of aerobic respiration. We then saw how the Winkler method could be used in order to determine the concentration of oxygen in a sample of water. And if you do this before and after incubation for a set amount of time, you can find the difference between the oxygen concentrations, and that is the biochemical oxygen demand.